So in our grand finale of the course is chapter 16. It's where all the concepts from the entire course come together and result in a sequence of really beautiful theorems. Before we get into it, I want to do kind of a review of some of the concepts that we've seen before. Because as I said, like every single concept that we've seen from the course is going to make a reappearance here. So we sort of have to have all those items sorted out in our minds. So let me just start with functions. What types of functions have we seen in the past? Well, we have the one variable functions from Calc 1, and we've got one variable going in and one variable going out, and I want to keep track of the geometry of the functions. So we can sketch one variable functions in the coordinate plane, and they represent curves in two dimensions, right? At the beginning of this course, we saw vector functions, right? And vector functions were either functions in 2 dimensions or 3 dimensions. So a 2-dimensional vector curve looked like this, and then a 3-dimensional vector curve looks like this. And we've got one parameter or variable going in, and either 2 coming out or 3 coming out, depending on the dimension. Oops. And geometrically, what these things represented were curves in either 2 or 3 dimensions. So one input gives us a one-dimensional curve. That's at least the pattern I see in these 3 cases. And then when we got into chapter 15, we started seeing multivariate functions. And the multi there was referring to the inputs, actually. So we could have a 2-variable function or a 3-variable function. And we did all kinds of calculus with those functions, right? So 2 variables go in, 1 comes out, or 3 variables go in, 1 comes out. And the geometry was okay for the first situation, but not for the second, right? Like the 2-variable functions represented surfaces in 3 dimensions, but with the 3-variable functions, I don't know. I mean, you could imagine them as like three-dimensional surfaces in 4 dimensions, but it's sort of useless to say that because I can't draw it anyway. But like, for example, you could imagine the domain as a 3-dimensional object, and then the output would be like temperature or density or something like that. Okay, so that's where we've been. Where are we going? Well, we want to, if you look at where we've been so far, we either increase the number of outputs or increase the number of inputs from 1. In this chapter, we're actually going to do both. So we're going to increase the number of inputs and increase the number of outputs. And there are several contexts where this occurs, but we're going to start with vector fields. So vector fields is what we start with, and you can imagine vector fields as being a kind of function that has multiple inputs and multiple outputs. All right, so vector fields as functions. First, let's start with some notation. So we're going to assign vector fields function names, and to distinguish them from other functions, we're going to put a little vector on top. The book uses bold, but it's easier when I'm writing, especially to use a little vector hat to indicate that it's a vector quantity. So we understand that more than one variable are going to come into these vector fields, and more than one variable are going to come out. And this is how it goes. We're going to imagine, for example, in 2 dimensions, for a 2-dimensional domain of a vector field, 2 variables go in, like x and y, and then 2 variables come out in the form of a vector. So the 2 coordinates of the output are both going to depend on the 2 inputs. So the outputs are going to be represented with 2 functions. So we either write it in terms of I and j, or ijk in the case of 3D, or we can use our vector notation like this. And so as you can see here, two numbers are going in, x and y, and 2 numbers are coming out, an x component of a vector and a y component of a vector, and each of those components depends on each of the inputs. And of course, we have the 3-dimensional version. You can have 3 coming in, and then 3 dimensions coming out. And one of the things that you have to sort out is when a function is given to you in this form, you can immediately classify it as a vector field. Don't get it confused with our vector curves from earlier chapters or our multivariate scalar functions from chapters 14 and 15. So that is the notation. Now let me show you what type of real-world thing such a vector field could model. This shows you wind patterns on the surface of the Earth. And what they're actually plotting here is a vector field. Notice that, and it's sort of in motion, of course, but notice that at any single point of this plane, the map of the world here is a plane, at any point, there is a vector that is assigned. It's a little segment that has a certain length and has a certain direction. So if I took a static shot of that would really give me, an image of a vector field. But let me just focus on a couple different spots on the map. So let's come over here to Kentucky. I see some short vectors, right, that are sort of going down and to the right. And not only do I see the length and the direction of these vectors, but the map is also giving me some colors that help emphasize the length of these vectors. Apparently the blues and the greens are shorter and the reds and the oranges are longer. So if I come over here just to the west of Spain, I see some much longer vectors, and those are headed to the south and to the east. So these are definitely vector quantities that are like the outputs, and the inputs are the xy coordinates of the location on the map. So your inputs are a geographical location in 2D, and your outputs are two-dimensional vectors. That is a vector field. And you can see that plotting the vector field gives us so much information about what's happening, right? We can see these spirals that are happening in different places. We can see the hot spots have the high wind, and and it's a really cool thing. Okay, so we can see that vector fields can be useful in representing a quantity that is flowing across a two-dimensional space or even a three-dimensional space. Before we look at more examples, let's actually realize that we've seen some vector fields before. We just didn't know that they were vector fields. So, for example, if you've got a vector curve sitting in either R2 or R3, then we were computing at any point along that curve the unit tangent vector. Well, that technically is a vector field because it assigns to any point, let's say in 2 dimensions, any point in 2 dimensions, a vector quantity. And that vector quantity depends on both the x and y coordinate of the point. And the other vectors of the Frenet frame are also, they themselves can be considered as vector fields. So the other vectors in the Frenet frame, of course, are the normal vector and the binormal vector. Okay, real quick comment about those. Those vector fields have domains that are very specific subsets of R2 or R3. They're like a one-dimensional curve in R2 or R3. Typically, our vector fields are going to have larger domains. Say, for example, the gradient of a function. Now, this takes a little bit of thought, so let me parse this a bit. If you've got, let's say, a two-variable function, gxy, then that's one of our sort of old multivariate functions. 2 inputs, 1 output. We geometrically understand this to be a surface in 3 dimensions. However, when you compute the gradient of such a function, what you're doing is you're assigning a vector quantity to every single point in the domain of that 2 variable functions. So what you do is you take the partial derivative with respect to x, and then the partial derivative with respect to y at xy, and you form a vector. And remember what that vector quantity represents. It represents the direction of steepest slope when you're traveling along the surface gxy, and its magnitude is the length of that steepest slope. But in this context, all I want to point out is that it is a vector field. Given any point in the domain, which is a 2-dimensional region, you are assigning a 2-dimensional output, a vector quantity output. So it is a vector field. Okay, let's just practice, using the definition of some vector fields to get a sense of what the vector field looks like. So I'm going to plot a couple vectors by hand, and then I'm going to go over to Wolfram Alpha because it does a good job of plotting at least two-dimensional vector fields. So let's play around with this one. Let's kind of, to get a feel for this vector function, let's sort of plug in some inputs and see what kind of outputs we get. So let's put in the 0, 0 point into this vector field and see what kind of vector we get out. Well, the x-coordinate of the vector field is the x-coordinate of the input, and the y-coordinate of the vector field is the y input. So the output of 0, 0 is the 0, 0 vector. Let's do another one. If I input 1, 0, I get out 1, 0. And if I input 0, 1, I get 0, 1. And let's just do one more. Let's put in 1, negative 1, and I get the vector 1, negative 1. So if I was to plot this vector field manually, then what I would do is I would draw a 0 length vector at the origin. And then over here at the point 1, 0, I would draw a vector that has x-coordinate 1 and y-coordinate 0. So let me do that in a different color. So there you go. I've just plotted f of 1, 0 right here. It's that vector. And we draw it emanating from the point that it's attached to, its input point. Okay, at 0, 1, I need to draw the vector 0, 1. It's got an x-coordinate of 0 and a y-coordinate of 1. So it would look like that. And then lastly, at 1, negative 1, that's down here, I'm going to draw the vector 1, negative 1, which goes over 1 and down 1. Okay, so this is some sense of what the vector field looks like. Let me put that 0 vector at the origin. But it's sort of time-consuming to draw all these. So let me go over to Wolfram Alpha, and if you just put in plot a vector field, it will give you some fields to fill out for your vector field. If you just put between curly braces the x component of your vector field and the y component of your vector field, which in general are functions of x and y, and give some limits on the variables, then it will plot it for you. So we had plotted 3 of these vectors, but it's giving you a sense of what the vector field looks like. Notice, for example, that the lengths of the vectors are getting longer as you go away from the origin, and they're smaller when you're closer to the origin. Okay, so here's a more thorough picture of the vector field. Okay, so let me just go ahead and fill out these other vector fields by plotting some points and then going over to Wolfram Alpha to get a better image. And I encourage you to work as many examples by hand as possible so that you get the feel for how the input-output rhythm goes. So I'm just, again, choosing a few ordered pairs to plug in, getting a rough sense of what the vector field looks like, and then I go to Wolfram Alpha. Here, the components of the vector field are x and negative y. So I put those in the curly braces, and Wolfram Alpha gives me this nice image. In this last one, observe that 0, 0 is not in the domain of this vector field. And not only that, but every single vector that comes out of this vector field has magnitude 1. And you can see that in the form of the vector field. You've got this scalar division by square root of x squared plus y squared. Anyway, that means that this vector field is attaching a unit vector to every single point in the plane, and they're arranged like this.